we'd like to start by considering an LC circuit, a circuit with a capacitor and an inductor. And let's find the expression for the current in the LC circuit. So the first thing we'll have to do is decide on directions of charge and current flow. I'm going to begin by assuming this plate is the positive plate, so that when the switch is closed and current is allowed to flow, the current will initially flow this way. Okay, so there's my beginning. The next thing I'm going to do is write down Kirchhoff's potential law. So I'm having my current flow clockwise around the circuit. My Kirchhoff's potential law says that the potential across the capacitor plus the potential across the inductor equals 0. So C equals the capacitance and L equals the inductance. This stuff is coming pretty new, so we'll try and stay on top of defining things as we go. Let's remember what the potential across a capacitor is. That's the charge on the plates at any given time divided by the capacitance C. The change in potential across the two ends of an inductor is minus L di dt equals 0. The two things we've written down now are Q, that's the charge on the capacitor, and I is the current in the circuit. Of course, Q and I are at some specific time t that we're talking about. In this equation, we sort of have two unknowns, but not really, because current and charge are, of course, related. So let's try and get to that relationship between current and charge. We know that current in general is change in charge over change in time. I'm trying to be really careful here with my symbols. Q is the charge on the capacitor plate. dQ is a little bit of charge moving through the circuit. How is this dQ related to the charge on the capacitor plate? Well, what we know is that dQ, the little bit of charge, the moving current, is equal to minus dQ. Okay, so what this means, and we used this idea before when we talked about how to find current for a capacitor, what it means is that current flows in the direction shown when the charge on the capacitor decreases. So current flows this way, dQ moves this way. If this amount of charge gets smaller, so that's kind of a small thing, but it is actually pretty important because we don't want to get mixed up in our signs and what's moving where. So that tells us that the current in the circuit is minus dQ dt. We get the current flow when that capacitor charge is decreasing. Okay, let's bring that back to this equation. Q over C minus L d by dt of dQ dt equals 0. This can simplify a little bit. This is going to be our second derivative, Q over C minus L, second derivative of Q with respect to time. Okay, this is something we can deal with. So I'm going to ask, does this equation look at all familiar? And if it doesn't just yet, why don't we simplify it one step further? Let's get our dQ dt on one side. Let's get our derivative on one side and everything else on the other side. So if we wanted to get our dQ dt on one side, our derivative on one side, we would have the second derivative of charge with respect to time equals, I'll bring my Q over C to the other side and divide both sides by L Oh my goodness, I dropped a minus sign. Okay, back up if you were following me. In our equation, Q over C minus L di dt equals 0. So we were good to here. I is minus dq dt. When I filled that in for I dropped my minus sign. Okay, so now this one is right. Minus times minus gives us a plus. And now we can arrange this guy for the second derivative in charge. So to bring the Q over C to the other side, that becomes negative. And divide both sides by L, we get minus 1 over LC times Q. There's our expression for our charge as a function of time in our circuit. So this is how the charge flows. And after we get our charge sorted out, we'll be able to find our current. So that's how the charge flows. So if we're asking the question, does that look at all familiar? If you can't think of the similar thing right off the bat, I'll remind you that this looks a lot like what you did in a first-year physics course with springs. So for springs, the spring force was minus kx, and force, of course, is mass times acceleration. Acceleration is the second derivative of position with respect to time. So that gave us that the second derivative of position with respect to time was minus k over m times x. The solution to this equation is one you probably remember. It's what we had for simple harmonic motion. Position of a simple harmonic oscillator as a function of time was some maximum position times cosine of omega times t, where omega is the angular frequency, was the square root of k over m. And then we know lots of things about angular frequency, such as it's 2 pi times the frequency, or 2 pi over the period. Okay, so this was some things we knew about springs. This equation and this equation has exactly the same form, so it has the same form of a solution. So let's write down what the solution is for the charge on our capacitor. So it means that the charge, the solution, the charge as a function of time is some value q0 times cosine of omega times t. Here, omega, here it was root k over m. Here it's going to be root 1 over LC. And that's the angular frequency of our discharging circuit. It's going to have the same relationships of 2 pi f and 2 pi over t. And q0 is the charge at time equals 0, and it's going to be the initial charge or the maximum charge. So now we might think about how does that charge change over time. And probably you would be able to know this just by thinking about it because you know what a cosine does. But if t is equal to 0, q is equal to q0 times cosine of omega times 0 equals q naught. If t is at a quarter period, then q is equal to q naught times cosine of 2 pi over t times t over 4. Why don't we write that one down? So here omega is 2 pi over t times period over 4 gives us 0. If t equals 1/2 of a period, then q is equal to q0 times cosine of 2 pi over t times t over 2, or cosine of 2 cosine of pi, which is going to give us minus q0. If t is 3/4 of a period, then q is back to 0, and at a full period it's back to q0 again. So if we wish, we could draw this on a graph. Well, yeah, why don't we draw it and then we'll come back and make a note here. So at t equals 0, the charge is at q0. at a quarter of a period, so this will be our period here, it's t over 4, t over 2, 3t over 4, t, and t over 5t over 4. So at 0, it's equal to the maximum. At a quarter period, it's equal to 0. Goes down to the negative maximum, minus q0, back up to 0, up to a maximum, and then it just oscillates over and over. So that's our charge as a function of time, and this refers to the charge on the upper plate. So oscillates over time. So there's the period of oscillation of an LC circuit. And Q is how much charge is on the upper plate at any time. So that deals with charge. We said we were going to use charge to sort out our current, so let's do that part next. So if we want to find current, what we know is I is equal to minus dq dt. We'll fill in our expression for Q as a function of time. So what we had for our charge, we'll fill in this equation for charge. So we have minus Q0. The derivative of cosine is minus sine. I always forget that for a moment. Then we have to take the derivative of the argument. Derivative of omega t is omega. That leads us to I is equal to minus times minus is a plus. Q0 times omega times sine omega t. This equation is fine as is, or you could write it as I equals I0 sine omega t, where I0 equals omega times Q0 equals the maximum current of the circuit. So if we wanted to draw this on a graph, we certainly could. So our current will go back and forth between I0, and it will go as a sine function. Just grab our graph paper again. So current as a function of time goes as sine. So sine starts at 0. A quarter of a period later, it gets to a maximum. So that shows us what we talked about in the beginning. After a quarter of a cycle, we hit a maximum current. Then at a half of a period, t over 2, it goes to 0, goes down to the negative maximum. That means that the current has turned around, is flowing in the other direction. That's at 3t over 4. At one period, it's back to 0, and then it begins again. So that's how the current oscillates over time. So something that's interesting to add, and this just gives us an idea of why these are such important circuits. If you remember, when we had simple harmonic oscillators like masses on springs or simple pendulum like a swing, if you drive an oscillating system at its natural frequency, at omega equals root k over m, so you apply an external force which also oscillates the same frequency, what you get is resonance. So these are cases when you can get the kid on the swing to go really high, when you can cause the Tacoma Narrows Bridge to oscillate with really big amplitudes of oscillation and it falls apart, things like that. So if you drive a system at the natural frequency of omega, you'll get a big amplitude of oscillation. Same thing happens with an LC circuit. So LC circuits, just like a circuit you would have in your phone, it's driven by a signal, an electromagnetic signal, which is picked up by an antenna. if the signal oscillates with a frequency equal to the square root of 1 over LC, you get a big amplitude of oscillation in the response. The other frequencies also have responses, but they just don't get that resonance. They don't get the big amplitude. So when your cell phone picks up a certain signal, that signal gets the biggest response. That's what you hear. Or on TVs, that's what you see. So it's kind of interesting that that kind of a driven frequency happens in exactly the same way. We still get resonance and things like that. Okay, next we're going to move on to a few examples.